For our assessment task 2, we are focusing on developing a database for the Australian Agricultural Company.
So we're working with the Australian Agricultural Company, and our objective is to implement a clean 3NF relational database that maps directly from our EER and UML models and runs in SQLite Studio. The scope covers the full chain of the stations, herds, cattle, processing, logistic, and sales. So every event is traceable from paddock to product. So the Australian Agricultural Company operates at a very large scale, but they do it with a robust model, and they get like out of date info and duplicate records, listing errors across a complex supply chain. Our database directly targets these two root problems.
So for our project objectives, we want to create a database that firstly effectively tracks cattle throughout their production cycle, so from the arrival at the cattle station through to the processing at the slaughterhouse or production plant. Secondly, we want to make sure that our database provides insight into sales and logistics through the tracking of order and shipment details. And thirdly, we want to ensure that we provide up-to-date data by removing duplicate values and maintaining and storing all data records effectively.
So for the requirement gathering process, we started by identifying the company context, as in the livestock, and the end goal: track cattle from start to finish and sell. Because the company is large, the database must scale accordingly. We mapped who uses it: warehouse, logistics, farm managers, sales, field and plant workers, and listed what data they input at each step. Finally, we researched industry workflows to keep the model realistic. So, functionally, warehouse tracks orders, managers oversee arrivals, departures, and shipment weight. Field workers record and view cattle details. Sales see orders and cut level stats, and plant workers update the processed status. Non-functional ones are handling like 5 years of data, restrict edges of sensitive info to management, skip a simple interface for farmers, fill stop and support adding new stations in future.
So this is pretty much a breakdown of the user requirements for the database. So this is a basic image of the EER diagram that we've created for our database. We'll be talking about that a little bit more in the next few slides. So here's a bit of the breakdown for the entities. So we have our supplier entity, which has the attribute as like a supplier ID, which would be the primary key, the name, the state, and the address, and it would have no foreign attributes. For the cattle entity, it would be the cattle ID, birth date, arrival weight, sex, breed, current weight, status, and arrival date. And for the foreign attributes, it would be the herd ID and the supplier ID. For the herd one, it would be herd ID would be the primary key, and a cattle count. And we would have, for the foreign attributes, the station ID and the cattle ID. For the station, it would be the station ID, the name, and the address, and the foreign attribute would be the herd ID. For the shipment, shipment ID, purpose, so as in why are we shipping it? Are we shipping it to as it's an order, or are we shipping it to be like a cattle to like a processing plant? The departure date and the arrival date of the shipment. This would contain the cattle ID, order ID, and truck ID. For the truck, it would just be the truck ID, number plates, and capacity, and the foreign attribute would be the driver ID. For the driver, it would be driver ID, name, contact number, license number, and we wouldn't have any foreign attributes. For the processing plant, it would be the plant ID, the name, and the address with no foreign attributes. The carcass would be the carcass weight, the carcass ID, the weight, the processing date, and the foreign attributes would be the cattle ID and the plant ID. For the meat cut, it would be the cut ID, cut type, grade, and weight, and for the foreign attributes, it would be the carcass ID and the plant ID, just so we can keep track of which carcass has been processed and which plant it has been processed at. For the customer, it would be customer ID, contact information, such as like a number, a name, and a delivery address, and there would be no foreign attributes. For the order, it would be an order ID, order date, type, as in would it be an overseas order, or would it be in normal national order, or would it be, and also the delivery address. And these would contain the customer ID and the cut ID, because we would assume that the orders that they're placing would have specific cuts of meat. So this is the relationships and cardinality for the ER diagram. So the supplier supplies the cattle. This is a one-to-many relationship, as one supplier can supply many cattle. The cattle is then assigned to a herd, and that is a one-to-many, as one herd contains many cattle, but only cattle can only be assigned to one herd at a time. So the herd is located at a station. This is a one-to-one, as one location can only have one herd. The station then uses the shipment. This is a many-to-many, as many locations or stations can make many shipments. The shipment contains cattle, so this is a one-to-many relationship, as one shipment can contain many cattle. The cattle then arrives at a processing plant. This is a one-to-many, as one slaughterhouse receives many cattle, but the cattle can only, one cow can only be processed at one slaughtering house ever. So a processing plant yields a carcass, which is a one-to-many. So one processing plant can produce many carcasses, but a carcass can only be produced at one processing plant. A carcass yields a cut of meat or a meat cut. This is a one-to-many, as one carcass can yield many different cuts of meat, but those cuts of meat would only particularly come from one carcass at a time. A processing plant, a order contains a meat cut, which is a many-to-many, so one order can contain many cuts of meat, and the meat cuts can appear across many different orders, so many different types. So someone might order like a sirloin steak, but two different customers order that steak. So a customer creates an order, which is a one-to-many. Customers can create many orders, but an order can only be assigned to one customer. An order then creates a shipment, which is a one-to-many relationship. So a shipment contains many orders, but an order can only be a part of one shipment from this company. The shipment is then assigned to a truck, which is a one-to-one. Each truck can only have one shipment at a time, and each shipment can only be assigned to one truck. The driver then is then assigned to a truck, which is also a one-to-one, as each driver can only be assigned to one truck at a time, and one truck can only be assigned to one driver at a time. This is the UML diagram for our assessment task. We'll go into that in a little bit more detail in the next slide. The UML diagram multiplicity is as follows. So the supplier to cattle is one-to-many, as each supplier is linked to many cattle, but the cattle can only be linked to one supplier. Cattle to herd is many-to-one, as a cattle is linked to one herd, but a herd can have many cattle. Herd to station is one-to-one, as each herd has exactly one station, and one station can host only one herd. Station to shipment is many-to-many, as a station can make many shipments, and shipments can involve many stations. Shipment to cattle is one-to-many, as a shipment contains many cattle, and the cattle are only part of one shipment at a time. Cattle to processing plant is many-to-one, as a cattle is sent to the processing plant for slaughter, only one processing plant, and a processing plant handles many cattle at a time. For the processing plant to carcass, it's one-to-many, as a processing plant produces many carcasses. However, a carcass can only be produced by one processing plant once. Carcass to meat cut is one-to-many. A carcass can produce multiple cuts of meat. However, each meat cut can only come from one specific carcass. Order to meat cut is many-to-many, as an order can have multiple cuts of meat, and one cut of meat can be present across many different orders. Customer to order is one-to-many, as a customer can make multiple orders, and an order can only belong to one customer. An order to shipment is many-to-one, as a shipment can contain multiple orders, and an order can only be part of one shipment at a time. Shipment to truck is one-to-one, as the shipment can only be assigned to one truck at a time, and a truck can ship one shipment at a time. Driver to truck is also one-to-one, as one truck can only have one driver at a time, and one driver can only have one truck at a time.
So for the database, we have used the EER and UML model, and here is a working database. You can see as in SQLite, the single.SQL script is idempotent. It drops in existing objects, enables foreign keys, creates all tables, builds useful indexes, and inserts ample sample data. We validated the built-in SQLite Studio and then ran the 4 queries to confirm integrity and realistic outputs. Here is our first query, which lists all the end customers, and it can be used like we can swap the state to target any region and export results straight for a marketing campaign list. So this is our second query where a cattle is weighted between two days threshold where animals can be shortlisted very easily for shipment and processing. So this is our third query where it is basically logistics overview, which talks about the whole shipment scenario, operation dashboard. It shows all the shipments with station plan, track, and driver info. The fourth and the complex query, it finds all the animal unprocessed or processed after more than 24 hours, latest arrival date via subquery and Julian Reddit map. This creates a daily escalation list for flow lists and can be returned to match changing targets.
We face challenges in managing a large amount of livestock data and removing duplicate records. It also difficult to keep the data consistent across different uses while still designing a simple system that farmers and field workers could use. And another challenge was combining the needs of different departments within the short time we had. To make sure the database worked correctly, we ran data integrity checks to avoid duplicates and tested primary and foreign key relationships. We used sample SQL queries to check cattle tracking and sales data and also tested performance within 5 years of data. And finally, we validate the system with different user roles and ensured sensitive data could only be edited by managers. In the future, we plan to add real time cattle tracking using radio frequency identification and GPS. We also want to create dashboards for better insight, develop a mobile app for field workers, and strengthen data backpack and security. Predictive analytics and integration with external system will also help improve decision making and compliance.
We delivered a reliable 3NF SQLite database mapped from EER and UML with one file build, realistic sample data, and four proven queries. It fixes duplication and inconsistency today and gives a strong platform for dashboard automation and auditability going forward. Thank you.